All right. So, what's going on, folks? I'm going to go over some Rat 3 stuff because apparently you guys are getting confused on this stuff. And I don't think it's so bad, but hopefully we'll check. Maybe I might have gotten the answers wrong. And then I definitely want to cover some Rat 5 stuff because that's going to be coming up pretty quickly, all right? So, I will do a few of these problems for you to help you out. Essentially, let's look at this one right here. 2x squared over 5x cubed. Got it? We can approximate. Okay, this one was easy. You don't want me to do this one? All right, fine. See, you can't be so dramatic and say I need you to do all of them when some of them are easy. You obviously there's some that are not that bad. Let's try this one right here. 1 over x and x squared. What does that graph look like? So that would look like, or I'm sorry, 2x over x squared. So that would look like the 1000 is irrelevant, the negative 3x minus 1 is irrelevant, and so you're left with 2x over x squared. You can graph that as 1 over x. 1 over x looks like this. Oh, oops. I didn't change the answer. That's the answer. It's that one. Well, if you graph 1 over x, okay. Let's see. If you graph 1 over x, that's what the graph looks like. So you know at the end behavior, it will look like this. That's why I chose that option right there. Genesis and Bradley, does that make sense to you? Okay, let's see. Essentially, you're graphing. What I'm saying here is this. What I'm saying is here, look. 2x plus 1000 divided by, wait, that's not what I want. 2x plus 1000 divided by x cubed minus 3x minus 1. Okay, so check this out. This blue graph is what they wanted us to graph. You guys got it? Now, that's the actual graph of the thing. And I ventured to say that that is very similar, or that the only relevant term in the polynomial that's in the numerator is the 2x. Do you agree? And the only relevant term in the denominator is the x cubed. Okay, Bradley does not agree with that. Okay, all right, fine. We can talk about that. Because, Bradley, here's the reason why. Let's take a look at that. X cubed minus 3x minus 1. I'm going to make a table. I think I can do it like this. There we go. Okay. So I made a table. And at 1, it's negative 3. At 2, the answer is 1, and so on and so forth, okay? And all right, so here's what I'm going to do. Is what I'm venturing to say, okay, Bradley, is that this thing is essentially the same as this at really big numbers. When x, if I were to plug in x as a really big number, then this thing is essentially boils down to just that. And so here, let me go and do that. Let me put in a, so when you're looking at 0, obviously they're not the same. When you're looking at 1, they're not the same. They're not even really close to the same. When you're looking at x equals 2, they're not the same. But we're talking about the end behavior here. And when we talk about the end behavior, we're talking about really large numbers. So let's go with 10. Hey, those are pretty close, right? What about 10,000? Or maybe 1,000? Well, at 1,000, it's 0.9999999 times 10 to the 8th, where it's just straight up 1 times 10 to the 9th, which is essentially what it would be if you rounded this thing off. And if I put 10,000, Desmos just simply doesn't show enough decimals to show you the difference between the two. Those two are the same exact number. And the reason being is because this 3x and this minus 1 does make a difference. But when you're plugging in 10,000 and you're cubing that, that would be like you have a number that has a 1 with, let's see, 12 zeros after it, minus 3,000 minus 1. So 1, what is 12 zeros? I don't even know. I think that might be trillion. 1 trillion minus 3,000 minus 1. If I had $1 trillion and you subtracted 3,000 and you subtracted $1 off of it, I wouldn't really care about the 3,000 and the $1. Does that make sense? You would still say I'm a trillionaire. So that's what's going on. Essentially, what I'm doing, Bradley, is I'm graphing. This is the actual graph. And we don't want Desmos to do it. What we want to do is we want to just be able to pull out the end behavior right off the bat. So what I'm saying here is that essentially this thing is almost the same as 2x divided by x cubed. Now you would say, I know what you're saying. You're saying, oh, no. Wait. Is it 2x over x cubed? Oh, no. I'm sorry. There's a square here. So, I see what your problem is. I see. Okay. I think it's in the way I asked the question. All right, do you understand this part that I have so far? Now, I don't blame you guys for not liking the way I set up this homework. I actually agree with you guys. I see what you're saying here. But do you understand what I have so far? That's what I'm asking you that. Okay. And you understand how this thing is pretty much equal to 2 over x. You see how the black one and the blue one are the same. We can reduce that. Okay. But I think what you're saying is, wait a second. The end behavior of the black graph goes from underneath towards 0 and above towards 0, whereas for the actual graph, it goes above on both sides, and it tapers off to 0 as it goes further out to the ends. I see. Okay, all right. I'll tell you what. You know what? I think I screwed up in the way I designed this homework. The reason being is because when we look at end behavior, really what we're looking at is we don't necessarily know exactly how the graph approaches 0 from underneath and going up to 0 or from above going down to 0. But I think that the point we need to look at when we're talking about this stuff is what is the horizontal asymptote? And the answer is this simplification process will still tell you some good information. It will still tell you that this thing goes down to 0. It doesn't tell you exactly how it goes down to 0. So without Desmos, I wouldn't be able to know whether or not that graph came from above and went to 0 or came from below and went to 0. In fact, my intuition would tell me it came from below and went to 0. Right? But the fact of the matter is, whether or not it came from above and went to 0 or came from below and went to 0, it went to 0. So that's the kind of information you need to be able to glean from chapter 3. That's basically what I'm getting at here. So I guess you're right. Technically, this is the right answer right here. And how would you be able to get that information from this graph right here? Oh, that's tough. That's tough. That's an interesting question. I can tell you how I would do it. But, yeah, the answer is, I see where what your issue is. So how am I going to change this homework? I'll tell you what. Because really it's a problem with the design of the homework, not necessarily a problem with like the math, I'll give you guys the credits for this. I'll just go in and give everyone 14 credit or 14 points for trying this homework. All thanks to your questions. Do you guys see what I'm trying to teach you though? Maybe it might have been a poor homework design, but I'm really trying to teach you guys about the horizontal asymptote idea. Yeah, so the horizontal asymptote part is not necessarily hard. The hard part is, so what I'm saying is it's not hard to figure out where the graph goes to towards the end. The hard part is to figure out exactly how it does that, how it goes about doing that. And parts of that information, pieces of that information come from knowing about the vertical asymptotes, knowing about the horizontal asymptotes, and so on and so forth. Why don't we try this? I'm going to move on to chapter 5. I think this will build up your confidence. All right, so chapter 5. We're going to go backwards, and we're going to be looking at, and I'm going to say right off the bat, I apologize for giving you guys a graph that might have been bad then. Or not necessarily bad. I can see how that homework got confusing. I have to figure out a way to redesign that homework, but I can see where you're coming from. Okay. All right. So I'm going to look at this graph, and immediately I'm thinking that there's a fraction. Right? There's a vertical asymptote. Can you tell me what is in the denominator of this graph? Not just -4. You need x minus 4. Is that what you're saying? Okay. Now, where is there a 0 intercept? So the idea is I've been giving you guys equations and I want to get the graph from you. And now I'm going backwards. I'm giving you the graph. I want you to tell me the equation. Where are the zeros? Or where's a intercept? At 2. So what's going to go in the numerator? What should I type up here? X minus 2. Perfect. Now, let's zoom in. Does this graph look exactly like that graph? Well, it does. It looks pretty darn close. Let me just double check something real quick. Okay. So I have my x-intercept, which is the numerator. I have my vertical asymptote, which is the denominator. I would say it looks pretty close. Would you guys agree? In fact, if I did that horizontal asymptote check, then the numerator is x, the denominator is x. So as the thing goes out to infinity, this thing is going to go out to 1, right? Because it's going to be x over x is equal to 1. The last thing I would check is look at the y-intercept. What is the y-intercept of the original graph? .25? No. It's actually 1/2. Because look, from here to here is 2. So halfway is 1, and then half of that is 0.5. Which is good because that's the same as the y-intercept that I would get. And you can double check that by plugging in 0 into here, and then you'll end up getting positive 1/2. Does that make sense? So let's try a few more of these. Let's try this one. We'll try making this graph. All right. I see that there's probably going to be a graph that has a fraction. Why do you say a fraction? Well, because I'm seeing vertical asymptotes. Whenever I see vertical asymptotes, I'm thinking, oh, okay, it's going to have that graph thing. Or it's going to have a fraction. In the denominator, where are the vertical asymptotes? That's my question to you. At 4 and where? There's 2 of them. -5, perfect. So in the denominator, what's going to go in the denominator? X minus 4 and x equals 5. You mean x plus 5? Exactly. Okay. Now in the numerator, what is going to go in? What is a key to this picture that will tell us what goes in the numerator? It's got to be 0. Okay, fine. If I plug in a 0 in here, this is what the graph looks like. Can't be 0, my friend. 0 divided by anything is still 0, and so the whole dang line is going to be 0. Oh, I see. You mean like the horizontal asymptote has to be 0. Is that what you're saying? I see. So what you're saying is it could be x, but whatever it is, it has to be some degree that's smaller than the denominator. And the degree of the denominator is squared. So this thing can be x, but it can't be x squared. Because then the horizontal asymptote wouldn't go to 0, it would go to actually 1. So it is just x. Okay. I almost agree with you. Let me tell you this. Here's the problem I have with, before I completely agree with you, is look at the y-intercept. Look at the y-intercept of the graph and look at the y-intercept of our graph. Also, look at the x-intercept. Where's the x-intercept of the graph versus the x-intercept of our graph? These can't be the same. Come on, you guys, talk back to me. Let me know. Say, I don't know what you're talking about. I'm confused. Help me out here, people. Okay, okay. Remember, the x-intercept tells you what goes in the numerator. So, and that's been the same since the beginning of time. So that thing is going to have an x minus 2 up top. And look what it did to the graph. It kind of took the graph and moved it just a little bit so that your x-intercept is at 2. Your y-intercept is at 0.1, which I could agree with. That could be 0.1. So I would venture to say that this right here, this equation, is the graph. This equation is the equation that will give you this graph. Do you get it? All right. And then I'm going to play that dumb game where I say, all right, well, what's the answer? And then you would have to say, okay, well, let me FOIL out the denominator a little bit. So it's going to look like x minus 2 divided by x squared plus x minus 20. Right? These are the same thing. You can see because the graphs overlay with each other. But also, you guys know that, right? All I did was I FOILed out the denominator. And then I think I'm just straight up playing that ABC game again. Like A is 0, B is 1, C is negative 2, D is 1, E is 1, and F is negative 20. You guys see what I'm doing, right? That's to put the answer into the computer. You got to go through that extra step of foiling it. But hey, you get good at foiling. That's good for you. All right, let's try this one. So what do you guys think of this game that we're playing? Bad? Easy? Hard? Not bad? And this is basically all we're doing for Chapter 5. All right, let's try this one. I know I'm going to have a fraction. That's a given. What is the new? I'm going to go a little backwards here. What's the numerator going to look like? I'll give you a hint. It has 2 x-intercepts. And those x-intercepts are 2. So I'm going to have an x minus 2 up here and an x plus 1 here. Right, exactly. All right, let's talk about the denominator. What is going to go in the denominator? X minus 3. Good. X minus 3. And a what? X plus 3. Perfect. I would venture to say that you got the graph right off the bat. Would you agree that that looks like that? The only other thing you would need to worry about is, and I think we talked a little bit about this with parabolas, is sometimes your y-intercept might not look exactly like their y-intercept. And in order to take care of that, you would need to mess with an a value out in front. And what that would do is it would, if a is big, it's still going through that vertically stretching, vertically compressing game that we played. As we change this number, your horizontal asymptote changes, your vertical intercept changes. Your x-intercepts do not change, though, as you mess with this number. But in this case, a was equal to 1. So we don't even need it there. But I'm just letting you know that that's might be the only other complication in this thing. All right, let's take a look at this one. This one looks good. We're getting the hang of this. All right, I got a fraction. Let's talk about the denominator first. What's going in the denominator? I'm thinking there's going to be 2 parentheses. Come on, you guys. Help me out here. The denominator comes from the vertical asymptotes. All right, I'm going to have an x plus 1, I agree. And an x minus 4. Okay, good. What goes in the numerator? X minus 2. Okay. That's what I got. That does not look like what I wanted it to look like. Right? Ah, Bradley is suggesting that we make this x minus 2 squared. And why would you suggest that, Bradley? Okay. Because over right here, it kind of just kisses that spot right here. Now, there's an obvious thing that's wrong with this equation right here. Look at our graph. Look at their graph. What can we do to fix it right off the bat? Ah, there we go. Exactly, Cameron. This goes back to there could be an a term out in front. And let me put a little slider in for that a, so I can change a and see how the graph changes. Now, if a were negative, as you guys are suggesting, then I would agree with you. It looks very similar to what our graph looks like. So, you would say just take that and make it a negative in front. Agreed? Okay, what's wrong with just having negative 1 out in front? Ah, there is another number. Yes, very good, very good. We're pulling this thing apart. Okay, what's the other number? Our graph is too fat. I love it. I love the way you're analyzing it. Our graph is totally too fat. I would say that there is a negative 3 out in front. That would be, yeah, let's try that. Now, how would I get the negative 3? I'll tell you why. And this goes back to, I could definitely agree that the form of the graph was this, right? But then if you look at the y-intercept of this graph over here, it's at positive 3. And over here, my graph, my y-intercept is negative 3. So I want to do something where it will keep all of my vertical asymptotes the same. It will keep my y-intercept the same, but it will change that, or it will keep my x-intercept the same, but it will change my y-intercept from negative 1 to positive 3. Well, I should multiply the whole dang thing by negative 3. Because that would change see how your x-intercept still stays the same. Your vertical asymptotes still stayed the same. They didn't change. All we did was we vertically stretched this graph. Actually, we inverted it, we flipped it upside down, and then vertically stretched this graph. Agreed? And we got all that information, this -3, from knowing the y-intercept of the graph and then saying, well, what do I have to multiply my equation so that my y-intercept will match up with their y-intercept? A more mathematical way to figure that out would be to say something like a times this is equal to y is equal to a times that. And there is an equation, so I write this equation on my piece of paper, exactly what you see here. Y is equal to some number that I don't know what this is, times all of that, right? And then I say, well, I definitely know of one point that's on this graph for sure. That's at y is equal to 3, x is equal to 0. Okay? And then what I should do is just solve for a. And you'll find out that a is equal to -3. That's it. So that would be the more mathy way of figuring things out. Of course, we could have logicked our way through it, and we did. All right, it looks like I have to go to see my next class. I'll give you guys full credit for that homework thing. How was today's? I think that the next lecture I do, we're just going to basically go through and do more of these things. Like I said, as you guys do more of these, you get better at them. And you see kind of the point. And personally, I would use Desmos to help me with my homework. All right. Talk to you later. Okay, bye.